Freak out. What's going on? We are firmly in logarithms. We just did solving exponential equations, and a lot of that amounted to taking the log of both sides or using change of base. So there's the other part of the spectrum. We solved exponential equations, so it stands to reason we're probably going to have to solve logarithmic equations. And so that's what this video is about. There's different things you can try, different methods you can do. And again, it's kind of like the chapter 5 stuff. A lot of it just comes with experience. But once you've seen enough of them and you manipulated and solved enough of them, they really aren't that bad. So without further ado, let's get into these 4 examples. I'm going to switch my camera over. Solving logarithmic equations. Here's just a quick little list of things that you can try, right? There were different avenues to take. One of the things, one of our skills was to translate. If it's a logarithm, try writing it as an exponential. An exponential, try writing as a logarithm. A lot of times the answer just kind of falls into your lap. Next was the condense or expand. If we have 2 logarithms separated with blah, 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 fill in the blanks, we can kind of clean this stuff up, if you will, and things will happen for us. So it's just something we can try. Some of them are just common sense. So I'm sure there's some math property for it, the logarithmic property of equality, something like that. But sometimes we can just say if it looks like a duck and quacks like a duck, it's probably a duck. And then finally, algebra. Is there some factoring involved? Are there solving equations involved? Are there multiply by the denominator and conjugates? We're going to mix all these things together and solve up some logarithmic equations. So let's start with the first one. Example 1. Okay, I'm looking at it, and I'm going for common sense. If log base 5 of 2x, log base 5 of 2x is the same as log base 5 of 20, well, log base 5 of this is log base 5 of that. This and that have to be the same. 2x has to be equal to 20, and then we can solve it and say x is 10. Cool, we like that one. Let's do a bunch like that. Something I do want you to notice here and caution you on. Be careful. Okay, on this one, it kind of looked like, and we did in sort of a way, just drop the logarithms because it was a log, just a log on this side and just a log on that side. But here I've seen students try to do this and say log base 5 of 2x plus 1 equals log base 5 of x plus log base 5 of x, and drop the logarithms and just say, well, then 2x plus 1 should probably equal x plus 7. But it doesn't work that way, okay? We have 2 logs over here separated with addition, so we could condense these down and then maybe do the logarithm property of equality, but you can't just drop the logs unless it's a single log on this side and a single log on this side with the same base. Okay, so just be careful with that. All right, next thing, let's try one. How about this guy? Okay, it's not just a log over here, so I can't just drop the logs yet. Okay, we learned a property that said if there's a 2 on the outside of a logarithm, we can put it on the inside as an exponent. Cool. Now we can say, whoa, it's just log base 3 of this equals log base 3 of that. If those 2 things are the same, then this and that have to be the same. This is the point where we could just drop the log and say x squared has to equal x plus 6. Okay. Now to solve this, though, we're going to need some algebra 1 or algebra 2. We're going to subtract the x and subtract the 6 to move it over to the other side, get it equal to 0. It's a quadratic. We're going to factor it, and we are going to use the ZPP and set these factors equal to 0. So we get our answers. Awesome. 3 and negative 2. But if we go back to the original problem, we have to be able, these numbers have to be able to work. We have to be able to plug these numbers in and get a correct answer. And in this case, if I plugged in a 3, x equals 3, log base 3 of 3, that would be 2. Log base 3 of 9, that would be 2. That one works. But negative 2 right here, you can't take log base 3 of negative 2. That's impossible. The domain restriction was we can only plug in positive numbers in here. So we actually get to throw this one away and say, you know what? 3 is the only answer. Okay, you're not even allowed to plug in a negative 2. It will not work. Okay. Next one. Now we're going to get to some fancy stuff. I guess. It's kind of fancy. Log base 5 of that monster, quadratic, equals 2 plus log base 5 of x minus 1. Okay, you can hit pause. I would encourage you guys to hit pause on all these and try them out and see how far you get before you get stuck, or if you can go the whole way. But I'm going to keep going. I see log base 5s on both sides, so it makes sense to like combine like terms, if you will. I'm going to put all my log base 5s on the same side. So I'm going to subtract this log base 5 over to the other side, and it would look like this. Okay. Now we can start to like mush these together. Two logarithms with the same base, separated by a subtraction sign. I could mush those together with division. That was one of our log laws. So it would become log base 5, 2 logs became 1, of these arguments with division. Log base 5 of this equals 2. Okay, now from here, we haven't seen one of these yet, but hopefully you can take this step. I can't just drop the log like I did before. If it was log base 5 of 2, yeah, then you could drop the logs. But here, this is just a logarithm. We have to solve this equation. So one of the things we could try was the translation piece. I can write this logarithm as an exponential. Cool. The base is 5 to the second power equals that whole mess. And when I do that, went too far right there, I'm going to get this thing. This thing is now our algebra 2 land. I can say this is 25. I'm trying to solve for x, so I'll never be able to solve for x if it's down here in the denominator, so I will multiply this over to the other side with that 25, and it would look like that. I'm going to now distribute, move all my x's to the same side, factor, and solve. Right? We're factoring. A lot of algebra 2 here. It's been a while. There's the distribute. There's the move everything to one side. There's the factor. There's the solve. And what we saw in that last one still rings true. We need to plug both of these numbers in at the beginning and make sure we're not breaking any rules, that they're checking out okay. Okay, let's try plugging in a 27. If I come up here to the top and plug in a 27, log base 27 minus 1, let's log base 5 of 26. That's okay. That's some number. I'm okay with that. Log base 5 of 26. But if I plug in a 1 right here, 1 minus 1 is 0. And log base 5 of 0, no bueno. You can't do that. So we get to throw this number out, this solution out, and say 27 is my only answer. Not too bad. Hanging in there? Good. Okay. Last one. Let's solve this guy. The log of x squared plus 1 equals 1. Okay. Hit pause, try it out, bring it on back. Have a log on one side. There is a base there. It's a base of 10. It's just invisible. We call it the common log. I'm going to translate. It's a logarithm, so I'm going to write it as an exponential. 10 to the first power equals that thing. Now we can solve this guy. I don't need to factor in this case. This would be like the square root property. I'm just going to subtract 1 to the other side and then take a square root, right? You only need to factor when there's an x squared and an x. So x squared plus 4x plus 4, I would have to factor that thing. But if I just had x equals 0, if I just had x squared minus 1 equals 0, you don't need to factor that. You could, but I wouldn't need to factor. I can just add 1 and then take a square root. And that's kind of where we are here. So I get this. I'm going to subtract 1 from both sides. X squared equals 9. Take a square root. That'll be plus or minus. If you have to put a square root symbol on a problem that's not already there, you would have to put the plus or minus symbol. So we get a positive 3 and a negative 3. We should check them. Okay? It's not just always throw away the negative one. Sometimes they work, and in this case they do. If I come up here and plug in a 3, I would get 3 squared 9 plus 1, 10. The log of 10 is 1. If I plugged in a negative 3 squared, still 9. 9 plus 1, 10. Log of 10 is still 1. So those actually both work in this instance. We don't have to throw either of them away. Okay? A lot of different avenues, a lot of different ways that we can attack this. And you notice as pre-calculus moves on, it just keeps building on things that you did in Algebra 1, things you did in Algebra 2, things we did in the first semester or the first part of the year. We just keep building on them and using them. So we got to keep up with that stuff. It doesn't just lay dormant in our brains and go away. We have to keep using it for it to stick and be good with it. Okay, so I should have mentioned this in class, or if you're not in class. That 10 might shrink to an 8. I haven't decided, but here's what it is. Here's a stamp that's not a stamp. Page 336, 27 through 46, and 55 through 70. Not Friday anymore. This is last year's, and probably not 10 problems. But we are going to, I'm going to pick some problems, and these are the ones you're responsible for. Okay? I'm not saying you have to do all of them. I'm not saying you have to do any of them. You practice as many of these as you want until you feel comfortable that you can solve any of those types of problems. And then on Monday or Tuesday, depending on what group you are, we are going to have a quiz based on these problems. So it's not a stamp. I'm giving you guys some responsibility here. Do with it what you will. You should become familiar with those. Call it a suggested stamp, if you will. I suggest you do those problems and be good at it. All right. Peace out. I'll see you guys.